Now we're going to look at polynomial functions, but these polynomial functions are going to have a higher degree than 2. So we're going to look at a polynomial function that has a power of to the third power, the fourth, the fifth, and so on. And we're going to find out that a lot of the things are going to be similar. There's just going to be a few differences we need to look at. And keep in mind, when we're talking about a polynomial function, and we look at the graph of a polynomial function, the graph is always going to have a smooth and continuous curve. So for an example, the graph is always going to be nice and smooth, and there's going to be no gaps or anything, no breaks in the graph. So it's going to be nice, smooth, continuous curve. If we have a graph that has a gap, such as this here, notice here there's actual gap or break in the graph. So for a polynomial, you will have no gaps or no breaks in the graph. Also, you will have no sharp turns. And what that means is we looked at some absolute value problems before. There's no sharp V into it. So all of these uh, types of things are not going to be polynomial functions. A polynomial function is always going to be smooth and continuous. So we want to look at a couple examples of some monomial functions to start off with. And if we say monomial, that means we're looking at one term. A monomial function has one term. And I'm going to review a little bit. We looked before at y equals x squared. And we know the graph of y equals x squared is a nice parabola that opens up, has a nice U shape. Then what's going to happen if we look at a higher degree other than y equals x squared? For example, what happens if we look at, let's say, y equals x raised to the fourth power or maybe the sixth power? Well, we're going to notice that if we just have this one single term, if we're raising it to the sixth power, what's going to happen is you're going to have the same similar parabola, but as we get closer down here to the x-axis, the graph is going to flatten out. And I'm going to exaggerate this a little bit. You can always put this in your calculator, and your graph is going to come down here and it's going to flatten out as we get closer and closer here and then go back up. Now, I do want to point out again, I'm really emphasizing down here at the bottom that the graph down here flattens out, but I want you to realize that it doesn't form a straight line down here. What this is happening is it's getting really, really close. So this is always decreasing until we get to the origin here, and then the graph slowly increases. Where for the x squared, the graph is decreasing all the way down here to the origin, and then it increases more rapidly. It decreases and then increases more rapidly than the x to the 6. So as this graph comes down here with x to the 6, it's still going down ever so slowly, but it's decreasing at a slower rate. So that's why we have this part of the graph here at the bottom. It really flattens out a whole lot more. And you're going to find out the same thing is going to happen the larger you make this exponent. So if you made this x to the 10th, then the graph is going to come down here and really flatten out really close to the x-axis and then go back up. Now, what do you think is going to happen if we were to do the same thing, but now instead of having even power, what if we looked at y equals x cubed, where we have an odd exponent? Well, we know the graph of x cubed kind of has this little bend in the graph like this. So what's going to happen if we look at y equals, let's say, x to the fifth power, okay? We have an odd exponent. Well, the same thing's going to happen again because of this exponent. The closer we get to 0, the more the graph is going to flatten out. So it's going to come up and again kind of flatten out a little bit and go back up. Now, once again, this is not a straight line. This line is not running right on the x-axis. The only point that this graph touches the x-axis is right at the origin at x equals 0. It's just that this graph is getting ever so close, it really looks like it's really flattened out. So keep in mind, it's just getting really, really close. And the reason that's happening is, for example, if you were to plug in and make a table, if you let x equal, let's say 2, oops, I'm sorry, and, well, if we let 2, of course, then y is going to be 8. But what happens if we let x equal, let's say, 1/2? Well, then we're going to get 1/2 cubed, which means we're going to end up with 1/8. So what's happening is as x gets closer to the origin here, where x is 1/2, your y value is 1/8. And then if you go to, let's say 1/4, then you're getting 1/4 to the third power. So notice your fraction's getting even smaller. And what's happening down here, when we do the same thing, if you were to just pick some values for x, uh, again, we could plug in 1/2, but now your y value is going to be 1/2 or 1/2 to the fifth power. So what's happening is notice your fraction is getting extremely small. So at 1/2 here, you're at 1/8, and down here at 1/2, your y value is at 1/2 to the fifth, which you would end up with 1/32. So this is 1/32. So you can tell here that you're getting extremely close to the x-axis because your y value is getting much smaller as we get closer to the origin. So that's why it appears here this graph is really flattening out the closer we get to 0. Now keep in mind all of these monomials, these one-term functions here, if we were to think of the transformations we've done in the past, for example, if we just look at this y equals x to the 6, well, we know that y equals x to the 6th, flattens out and touches here at the origin. Now, what happens if I said we have y equals x, let's say, plus 2 raised to the 6th power? Well, the same rules we had for transformations going to apply here. Notice now, where's this 2? The 2 is on the inside, so that's going to move your graph left or right. Because it's on the inside, it's going to go the opposite direction, so we're going to move 2 units to the left, and we're still going to have this same basic shape where the graph comes down, it flattens out now. Instead of at the origin, it's going to get closer and flatten out at -2, and then it's going to go right back up. Okay, and then the same thing would be true if we looked at something like y equals x to the 5th. Let's say that we change the graph around a little bit, and we have y equals, let's say, x to the 5th plus 3. Well, we're going to have the same basic graph, except for now the 3 is on the outside of the function, and keep in mind what effect does that have? That's simply going to move the graph up 3 units. So here, again, your graph is going to go up, and then it's going to flatten out here, and then continue to go up. So all those rules of transformations we learned in the past are going to still apply in this situation. All right, we want to look at what's called a leading coefficient test. And this is going to help determine what's happening at the far ends of our graph. Now, keep in mind, if we looked at the function, the polynomial here, we know the form of it is a sub n x to the n plus, and then this kind of continues all the way down where we would have, let's see, a n minus 1, x to the n minus 1. And all this means is x to the n, your exponent. If this is x to the 5th, then the next one's going to be x to the 5th minus 1, so you'd have x to the 4th. So here your exponents are simply going in descending order. I know this looks a little strange with the notation. And you're going to go all the way down to you have a sub 1, x to the first power, and you'd have a sub 0, and you will not have an x term because your x term would be x to the 0, and if you have x to the 0, that's simply going to be 1. Well, if you have your polynomial function here in descending order. Keep in mind here, these a sub n, this just represents the term here, and a is representing the coefficient of your polynomial. And the exponent here is the largest exponent, the x to the n. So the coefficient here that is with the largest exponent is called the leading coefficient. Now, as long as you have your polynomial in descending order, where you have your largest exponent first and then the next one and then so on, this first piece is always going to have your leading coefficient. Okay, that's the a sub n. And then, of course, the n here is representing our exponent. Okay, and again, if it's in descending order, this is going to be the largest exponent. Now, how the leading coefficient test works is we're going to look at, obviously, the leading coefficient, and we're going to look at the exponent. And the way this works is in your book, they're going to give you kind of some notation here. It says that if n is even, so if your exponent is even, okay, and your leading coefficient is greater than 0, then what that tells us, if you look at the graph, your graph at the far end at some point is going to be pointing up to the left, okay? Or it may say that it rises to the left. So your graph is going to be pointing up to the left. Now, we don't know what's going to happen in between, but then over here at the far right, your graph is going to also be pointing up to the right or rising to the right. And that's going to happen anytime that your exponent is even and your leading coefficient is greater than 0, which means your leading coefficient is positive. Okay? Now, if n is even and the leading coefficient is less than 0, which means it's going to be negative, then that means your graph, instead of going up to the left and up to the right, the far ends are going to be pointing down to the left and down to the right. Or you may say the graph falls to the left and falls to the right. All right, then what's the other possibility? Well, what happens if n is odd? If n is odd, now what is n? N again is the exponent. So if your exponent is odd and your leading coefficient is positive, so it's greater than 0, what's going to happen to the graph? Well, because the exponent is odd, your graph now is going to be down to the left and pointing up to the right. So if you notice, if your exponent is even, the endpoints of the graph are going to be pointing in the same direction, either both up or both down. If your exponent is odd, your graph is going to be pointing in opposite directions. So in this case, because the leading coefficient is positive, it's going to point down left and up right. And probably you're smart enough to figure this one out. If you have a leading coefficient that is less than 0, which means it's negative, then you probably can guess what's going to happen. Instead of now going down left, the graph is going to point up to the left and then down to the right. So it switches directions. Now, you can memorize this. And I went through this because if you probably look in the textbook, that's how they're going to explain this to you. The way that I prefer to memorize this information is to think of it this way. Let me see if I can make this notation over here on the side. If we look at the equation y equals x squared, what does y equal x squared? What does the graph look like? Well, hopefully by now we know that if we graph y equals x squared, we're going to have a parabola, and we know that it's going to open up because our a is positive. Now, what's happening at these endpoints? They're going up to the left and up to the right. So if you can remember what's happening with y equals x squared, that's what this first statement is saying. If n is even, well, our exponent over here is even, The leading coefficient is positive. Our leading coefficient is a positive 1. So our graph is going up to the left and up to the right. So if you simply can kind of compare to y equals x squared, we know that the function here is pointing up left and up right. And then also, if we were to look at, for example, y equals a negative x squared, well, we know because of the negative sign, it's going to cause our graph to go in the other direction. Well, what's happening? It's pointing down left and down to the right. And that's what's telling us over here, it's going down left and down right. So I just like to think of if we have a even exponent and it's negative, I know that the endpoints are going to match with a negative x squared, so the endpoint is down left and down right. And then we can also compare this to y equals x cubed. I know by now we know the graph of y equals x cubed. It's the graph that has the little bend in the middle here. And keep in mind what's happening to the very end. Because this exponent is odd, over here we have an odd exponent. Leading coefficient is positive. It's down to the left, up to the right. And that matches over here, down to the left and up to the right. So then if we can remember what y equals a negative x cubed looks like, well, we know it's going to be just like x cubed, but because of the negative, it's going to give us that reflection. So now it's going to go this way, which means that it is pointing up to the left, just like over here, it's going up to the left, and down to the right here, just like it is over here. So you can choose to memorize, n is even, n is odd, the leading coefficient, or if you just remember what does x squared and x cubed do, and what does negative x squared and negative x cubed, then you can apply that to your other polynomial functions. So for an example, let's see if we can apply the leading coefficient test to the given function. Let's say that I give you the function f of x equals negative x to the fourth plus 7x cubed plus 15x plus 205. Now, the first thing is we want to make sure this function is in descending order. Well, if we notice here we have x to the fourth, x cubed. There's no x squared, so that's fine. And then we have x to the first, and then we would have our x to the 0. So we have our function in descending order from largest to smallest exponent. So now we're simply going to look at our first term here. We have a negative x to the fourth. Well, because the exponent is even, the way I like to think of this, I know it's going to be very similar to what we have if we have y equals x squared. We have an even exponent, okay? So that means both endpoints are going to point in the same direction, either up left, up right, or down left and down right. So the endpoints are going in the same direction. Now, we know that this is negative, so we know that it's going to look like a negative x squared. Well, we know the graph of a negative x squared is going to open down like this. So that tells us that if we were to graph this function here, the endpoints, now we don't know anything else about inside of the graph, we just know that at some point to the far left, the graph is going to go down to the left, and it's going to end up pointing down to the right. Now, you may think this isn't really important, but if you could easily put this in the calculator and determine. But if you put this in the calculator and you have to be adjusting your window screen to find out the correct size of the window, then you know that if you see your graph pointing down and then somewhere your graph is pointing up, you know that eventually that graph that's pointing up would have to eventually point down, because you know that the graph of this particular function, both ends have to eventually be going in the downward direction. So this is just a good idea to have a good estimate of what the end of the graph is possibly going to look like. Okay, now a little bit later in the next video, we'll talk about how we can determine what's happening, in between here. But right now, all we're looking at is what's happening to the far left and to the far right. So let's look at another example and let's see if you can determine what's happening here. So if I gave you the function, let's say h of x equals x to the 9th power minus 7x plus 3. Now, once again, all we're looking at is using the leading coefficient test to find out what's going to happen to the far left and far right of the graph. Well, if we look at this piece here, we notice that we have an odd exponent. So we know it's going to be similar to y equals x cubed. And we notice here that it is a positive. So we know the graph of y equals x cubed looks like this. So we know that the endpoints here are down left and up right. So if we were to graph x to the 9th minus 7x plus 3, to the far left it's going to fall to the left or go down to the left, and then the endpoint of the right side is going to point up to the right. Again, we can determine all of that just from this leading coefficient. Now again, it has to be in descending order, x to the 9th, negative 7x plus 3, so we know that it's going to go down left and up to the right.